let's now discuss how we learn ConvNets from data. And first we'll discuss how we can design ConvNet or ConvNet structures. And in fact, to be honest, this is actually quite some engineering task and essentially experimenting with different structures. And we'll discuss three prominent structures, in particular GoogleNet, ResNet, and DenseNet. And then we'll try to understand a bit better what kind of features ConvNets learn by looking at some visualizations of these features. And then in the end, we'll discuss training of ConvNets. And we will again use backprop, but now ConvNets are even more complicated than multi-layer perceptrons. So backprop is now more convoluted in convolution neural networks. And we won't go into detail, but we will draw a relation to multi-layer perceptrons. We'll link back to multi-layer perceptrons to understand how backprop works in ConvNets. And before we start, let's discuss the inductive bias in ConvNets. So we introduced the inductive bias as this idea of having a prior or a structure in your machine learning model, like the neural network, which makes your model more suitable for particular underlying data domains. And here the idea was that ConvNets are more suitable for signal-like data, in particular images. So what kind of inductive bias do qualitatively ConvNets have? So ConvNets have definitely implemented this idea of locality. So we have these convolutions, so with these convolutional filters, which slide over the images or the feature maps. And at each position, essentially, we can figure that the output, so the convolution at each position is essentially a neuron which has a local receptive field. So if we slide the convolutional filter over our image or our features, at each position we can figure that there sits a neuron which essentially just looks at this local receptive field where the convolutional kernel currently is. And so therefore these neurons neighboring neurons in a feature layer will therefore be looking at neighboring image patches. So these neurons preserve these strong local correlations, which is adequate for images because they have strong local correlations and strong local patterns. And also, ConvNets have a high degree of weight sharing. So if we perform a convolution, so we essentially slide one convolutional kernel over the whole image. And so at each position we have an output or a neuron sitting, and all these neurons essentially have essentially look at the same feature. So all these neurons essentially share the same weight, and this weight sharing makes essentially these features less sensitive to image translations. So if we translate the image a few pixels to the left or the right or the top or whatever, then you can always be sure that there will be some neurons essentially. So essentially this just translates to a translation of the feature maps, so of the high feature maps. So the higher feature maps have this preserve the locality of the original image, and therefore if we shift around the image, we essentially also shift around the higher feature maps. And now if we apply pooling, so pooling essentially summarizes some neurons in a small window, and if we apply max pooling, so therefore it doesn't really matter where the max in the window appears. Therefore, this pooling essentially increases this further translation invariance. So this weight sharing, so because neurons in the same feature map share the same weights, therefore we can be sure that if we slide the window, we are still detecting similar features, but just translated. And if we apply pooling, we're essentially increasing a translation invariance, which is good because if we translate an image, so if we shift an image, we would not expect that it changes, for example, its class. So therefore, ConvNets have a pretty good inductive bias for images and signals in general. So how do we build actually a ConvNet structure? So we've now seen several ingredients like convolutional layers, pooling layers, and fully connected layers. And actually, much of the performance of ConvNets, so ConvNets are state-of-the-art in essentially everything which has to do with images and other signal-like data. But much of this actually stems from engineers and scientists experimenting a lot with different designs. And this actually highlights that deep learning is a little bit of an engineering art or a black art. So essentially there's like no clear recipe of which structures will like work best. And essentially it's a lot of trying out and engineering and experimenting. So research papers which describe new structures, they do this often in a compact way, and we'll look now at a few examples of ConvNet structures and how these are often described in papers. So at this first example, so this is a rather small ConvNet. So often these ConvNets are illustrated with plots or graphs like this. And essentially this is just describing a stacked ConvNet structure where we start with an input layer, the image, and then we have a 5x5 convolution with 6 channels, and then we apply a ReLU non-linearity, then again a 5x5 convolution, but this time with 12 output channels, another ReLU, another convolution, another ReLU. Then we are doing a flattening and going into a fully connected layer with 256 neurons. So this flattening is not explicitly shown, but essentially after this ReLU you can figure that we flatten it into a vector and we go into a hidden layer, a fully connected layer with 256 neurons. And then we go into a softmax, a 10-fold softmax. So in order to train a classification problem with 10 classes. Or for another structure, so a bit more complicated, here we have essentially this max pooling blocks in between. So essentially this is just a different structure, and often researchers represent their structures with graphs like this. So these two examples, they were pretty regular and stacked. And so in recent years, scientists really experimented with more complicated structures. So this is, for example, GoogleNet. So here we start with the input, and blue boxes are essentially convolutional layers. And this network is too big, and therefore the figure is essentially too small to really see now the parameters of these convolutions. But and then we have pooling layers, and these green ones are either concatenation or batch normalization layers. And the speciality of this GoogleNet is essentially that they have these towers. So at some point, the structure would just divide into parallel structures. So here at this point, the output of this pooling layer goes through a convolutional layer, and parallel to that to another convolutional layer, two additional convolutional layers, here through a pooling layer, convolutional layer, and here through 2 convolutional layers. So here essentially some parallel processing happens, and here again everything is concatenated and normalized. So in this structure they have like this parallel processing or towers, and moreover they have essentially multiple readouts. So here is this classical readout, and here this would be, for example, a softmax with cross entropy, but they also mix this objective here with another objective, so where they have like an earlier readout head, so with another softmax layer and another cross entropy loss, and an even earlier readout with another softmax layer and the cross entropy loss. And then in total, this network is just trained by just adding these 3 losses. And so essentially this helps that lower layers essentially also get a strong training signal. So people are really creative with the structures, and so there's like no clear pattern how people came up with the structure. At some point it just turned out that this like really works nice for image classification, for example. Another structure is a ResNet for a residual net, and here the main idea is that they train quite deep convolutional neural networks, and here the speciality is these skip connections. So at some point they would just take the output and just like add it again a few layers later. And if you think about this essentially just means that the point here is actually just like this output plus this transformed the function of what we read out here. And essentially this means that these 2 layers here learn kind of a residual. So essentially this is the identity function plus some residual. And so this simple trick really made back then in 2016 allowed them to train like really deep neural networks. So essentially, so these layers are essentially interpreted as a residual. So because you just copy the current feature map just a few layers later, and then essentially you just add in a function of this feature map. So it essentially is like learning a residual relative to an identity function. And more recently, there has been DenseNet, which consists of these dense blocks. So these dense blocks get input, and in these blocks they have like several layers, like convolutional layers. And so this first layer would get just the input, but the second layer would get the input plus the output of the yellow layer. This green layer would get the input plus the output of the yellow layer plus the output of the red layer. So essentially this concatenates many previous layers as to a concatenated input, and essentially this seems to improve performance quite significantly. So people were creative with many different structures, and overall it's pretty hard to keep track of different structures and also different data sets. So I would invite you to look at this page. So let's look at this page together. So this page shows different image benchmarks. For example, MNIST. So we already had this. This was this handwritten digit benchmark, or Fashion MNIST, which has exactly the same format as MNIST, but has fashion items instead. There is CIFAR 100, which is an object detection task with 100 different classes. CIFAR 10 is the 10 class version. And the most challenging task is this ImageNet. So for example, if we look at, MNIST, so a simple learning tasks, and if we look at accuracy, for example, so we see that this task is actually solved. So it's a test accuracy of almost 100%. So I don't know why it's here only 98. So this is probably not correct. So like this task has been actually solved for a pretty long time. And so if we see it, like the leading method here is an CNN. So this is for convolutional neural network. And also, so the second method is an ensemble of CNNs. And the third method is again an CNN. So and VGG5 is also an CNN. I think this is something different. So CNNs really rule on these image data sets. And we can also look at ImageNet. So this is a very big data set with up to 20,000 different classes. And here people often report the top 1 accuracy. So the top prediction of the neural network, or like also the top 5 prediction. And here in top 5 accuracy, you get a correct classification if among the top 5 projected classes, the correct class is, there is the correct class. And here we see, over time, we see the improvement on this on the test set of this benchmark. So in particular here, 2012, we see AlexNet. We had this. This really kicked off deep learning quite significantly. And before that, we had this hand-designed visual feature design plus some machine learning method. And like 2012, convolutional neural networks immediately improved more than 10% absolute the performance. And since then, we have seen all kind of different networks. So here we see ResNet. We just had this residual connections, and so on and so forth. So it's fun to play with this site and check different benchmarks and how different methods compare. Check out the site. So this is interesting to explore. Let's now try to understand convolutional networks better by looking at the features they learn. And here I'm referring to a paper by Zeiler and Fergus, visualizing and understanding convolutional networks. And what they did is to train a ConvNet on this ImageNet dataset. So I briefly showed this benchmark on this web page. So this is a very large dataset with millions of features and images from natural scenes and natural objects. And so they visualized the features on each of these layers. So in each layer, they selected a few neurons or a few neurons and visualized the filters, the features they learned. And on the very first layer, so which comes right after the image, these filters can be directly visualized as images. So if you recall, when we discussed the convolutional layer, we had these kernels, for example, 5 times 5 times 3. And if we interpret them as image themselves, we essentially see the features they are looking for. So recall, the convolution or autocorrelation essentially is like a feature detector. So we slide these filters over the image, and where the image looks roughly like this filter, the neuron gets high or excited essentially. And what happens typically in convolutional neural networks is that this first layer learns like very simple or primitive features, like for example, these edges. So a typical thing is that it learns these edges. So these are different edges, but rotated ones. This is also an edge filter, but with a higher frequency. Or you have like these corner or blob detectors, or maybe area detectors. So here they visualized just the filter coefficients as image. And here they picked patches, so image patches from the validation set, which mostly excited these selected neurons here. So these are now real image patches, and essentially they looked for that exhaustively in the validation set. So for example, this image here excited this neuron here. So because they have like this, this strong edge here, or this image here excited this neuron here, this image excited this neuron here, these image here, so like with this high frequency edges excited this neuron here, these green patches, this neuron here, and so on. So this is like a technique to visualize the filters in the in the first layer, and like giving typical inputs which essentially excite these neurons in the first layer. So they did something similar for the higher layers. So for example, here for the second layer. But the second layer doesn't, we have a problem that we cannot directly visualize the filter weights here. So what they did is they selected some different feature maps, and they selected like the 9 most excited units in each of these feature maps. So we have just some randomly selected feature maps, and the most excited neurons, 9 neurons. And in order to visualize essentially the features these neurons learn, they did this with an optimization approach. So essentially they optimized for the input. So they optimized the input pixels in order to mostly excite these neurons. And here essentially we see this visualization here. So they optimized the inputs so to excite these neurons most. One thing to notice, so here in the first layer, so we have like, maybe this is like a 5x5 or a 7x5 convolutional window, which has like a pretty small receptive field. So like this is very localized. But since now the second layer takes a convolution of the first layer, the receptive field of the second layer is already bigger. So since it actually looks at the output of the first layer, and each neuron of the first layer has already a receptive field, so the receptive field becomes larger and larger the higher and higher we go in the neural network. And so, in the second layer, so they visualize these these artificial inputs which excite our neurons. So here we see the neurons still have like these rather low-level features like edges and like blobs and so on, but less primitive than in the first layer already. And here they present here typical patches from the validation set which excite these neurons most. So here we see like these blob features and edge filters, but already with more sophistication than on the first layer. And they did the same with the higher layers. So on the third layer, we see the receptive field of each of these neurons is already larger. And we see that these features here are now real patterns already. And even here, like this is already a peeper detector, so a pretty sophisticated pattern. Here, this is like essentially reacting to ladybirds and pumpkins and tomatoes or something like this. And we see on this third layer already, we have like pretty high level image semantic features. And this becomes more and more striking the higher we go. So in the fourth layer, even more large receptive field. And here we already have like a dog detector and like a roundness detector, and so these shapes become more and more complicated, and until the fifth layer. So here we see that these features are already pretty semantic. So this, for example, here we have a cat detector or an animal detector. Here another seems like a people detector, a flower detector. So like on this fifth layer, these features already have like pretty strong semantics. So this is how, this is the kind of features convolutional neural networks learn. So like from very low level and low basic computer vision features to more and more complicated and abstract features. So, and this is also the idea of ConvNets. And so with a grain of salt, ConvNets can also be compared to the visual cortex in the brain. So don't take this too serious, but when we look at the brain, so here we have the eye, and the visual input goes to the visual cortex, the V cortex, and it's actually confirmed by neuroscience on V1, so the lowest layer essentially of the visual cortex also reacts to simple visual forms like edges and corners and these kind of things. And the higher we go in the visual cortex, the more complicated these features become. So this is roughly similar as what happens in a ConvNet. And also pooling can be roughly identified with systems of inhibitory or competing cells, so where a winner-take-all system. So if you have like a system of cells where the cells try to maximize the output but try to inhibit other cells in the system, this is like roughly what max pooling does. So again, this is like with a grain of salt. So this is like very high level similarities what happens in the visual cortex as well. So, but yeah, with a grain of salt, please. And ConvNets really illustrate nicely a basic philosophy in deep learning, namely end-to-end learning. So we saw these ConvNets, they essentially are like a stack or a more complicated structure of conv layers and pooling layers and so on. And often at the top, we go back essentially so we flatten our features to a vector, and this gets then feed into MLP layers, or fully connected layers. And now this can be nicely interpreted as that this lower stack, so this ConvNet stack and pooling stack and so on, is essentially like a feature extractor, a trainable feature extractor. So, and the whole system can be, so on top of these MLP layers, so the whole system can be interpreted as this trainable feature detector plus a predictor, which are these fully connected layers, or the MLP parts. So the ConvNet part is like a feature extractor, and the MLP part like the predictor, so like a classifier. And now this whole pipeline, so consisting of ConvNet-based feature extractor plus multi-layer perceptron on top of this, is trained end-to-end. So the whole system is trained end-to-end with backprop, as we will see in a minute. And this is a pretty strong contrast of how people did this in traditional computer vision. So in traditional computer vision, people designed features by hand. So maybe most widely known before the deep learning area, the so-called SIFT features. So these were hand-designed features exploiting domain knowledge. And then people would use some machine learning tool on top of the SIFT features. Yeah, train some classifier, for example. Now in deep learning, in particular ConvNets, so this ConvNet feature extractor plus the predictor is learned simultaneously or together end-to-end. And so this end-to-end learning is one of the key philosophies in deep learning. And this has not only been successful in computer vision and image recognition, but also in other domains like speech recognition and language processing. So end-to-end learning, this is one of the key philosophies in deep learning. So we've mentioned learning. So how do we actually learn ConvNet? So we haven't really talked about this. And actually the short answer, well, as usual, and neural networks are trained with backprop nowadays. But in comparison to multi-layer perceptrons, backprop is now a bit more convoluted or complicated. Fortunately, you don't actually need to implement this, and you don't need to know this. So the short answer is use a machine learning framework like PyTorch or TensorFlow, and this already optimizes the backprop routines for ConvNets. So this is backprop is a bit complicated in convolutional neural networks. In particular, if you want to make it efficient, this is actually, well, pretty tough engineering task. So therefore, don't do this by hand, but actually just use existing tools. However, I want to at least discuss how this works in principle. So in principle, we can interpret ConvNets again as multi-layer perceptrons. And then in principle, it's the same backprop rule as in multi-layer perceptrons. And so this we will do this now. So we will now reinterpret ConvNets as multi-layer perceptrons, as fully connected layers essentially. And this will help us to understand how backprop now works in this a bit complicated ConvNets. This is not a way to really do this in practice. So this is really just targeted for principle understanding. So how does this work? So let's look at a simple example. So here we have just a 3x3 image. So with 9 pixels, x1 to x9 here listed in the rows. And it's just a single channel, so like, not RGB, but like a grayscale image. And now we convolve this with a 2x2 convolutional kernel with convolutional weights W1 to W4. And essentially what happens is you start with this window up top, so on the top left, and then you slide it 1 pixel to the left, then you go down here, and again, no, to the right, and go down here, and then you slide it again to the right. So you just slide this window over 4 different positions, and this gives you 4 different outputs. So here we don't apply zero padding, so we just apply the vanilla convolution, and we get like this, we have this 3x3 input, and we get this 2x2 output. And now if you now look at the details, what the output y1 is actually just given by x1 times w1, x2 times w2, x4 times w3, x5 times w4. So what is standing here? And so the next pixel, so if you move the convolution 1 pixel to the right, so y2 is just x2 times w1, x3 times w2, x5 times w3, x6 times w4. So what is here? So and the same for y3 and y4, so just with shifted window. So please double check that this convolution here indeed corresponds to this system of equations. So here the outputs, and we have x1 to x9. Now if we collect now the y's to a vector, the y, and if we collect these 9 inputs to a vector x, then it's then we can write the system of equations as this matrix multiplication here. So we have this matrix here times our input vector gives our output vector. So the same result, so convolution can be written here in this system of equations, and double check that the system of equations corresponds to this convolution and also to this matrix multiplication. So just writing the system of equations with a matrix multiplication gives us this this equation, so this vector matrix multiplication. And now we see that this weight matrix here has a special structure. So we see this staircase structure here popping up. So W3 and W4 and so on. So we see these staircases are popping up and a lot of zeros. And so this is something typical which happens when you apply convolution. So convolution can be transformed to a matrix multiplication with a so-called tuplets matrix. So this is one type of tuplets matrix which comes out of this convolution here. So convolution can be again written as a matrix multiplication with the input vector. And double check that this is indeed the same thing here. Now, recall in a fully connected layer, so like in multi-layer perceptrons, we saw, one layer is actually just a matrix multiplication. So we have a hidden layer, and we multiply it with a matrix, and we get essentially the activations of the next layer, and then we would apply a nonlinearity here. And now we see that the convolutional layer can also be implemented with a matrix multiplication, but the matrix has now structure. So a fully connected layer and the convolutional layer are both just matrix multiplications. And the only difference here is really that in a multi-layer perceptron, so a fully connected layer, this matrix is completely unrestricted, while for a convolution, so this tuplets matrix has strong structure, a strong sparseness structure because it has a lot of zeros, and it has shared weights because, for example, W1 pops up 4 times, and also W2 pops up 4 times, and W3 and W4. So we have sparseness, a lot of zeros, and shared weights, but otherwise they are both matrix multiplications. So fully connected layer, unrestricted, unconstrained matrix, and a convolution layer, a constrained matrix, sparseness and shared weights. And the same holds true if we have a larger convolution, but then the tuplet structure is just different. So convolution can always be cast to a matrix multiplication. So again, so like this convolution here can now actually implemented by a matrix multiplication. Just unroll your pixel vector here and multiply it with this tuplets matrix. And this indicates actually that we could actually now just learn this matrix like in an MLP or a fully connected layer with backprop. And now essentially the only challenges here are now the special structure of the matrix. Namely, we have a lot of zeros, so how do we learn them? And we have these shared weights here. So how do we learn a matrix with shared weights? So to answer the first question, how do we deal with the zeros? Well, easy. Just initialize them with 0 and never update them. Problem solved. So the more crucial problem is how do you treat shared weights? So if you want to learn a neural network with shared weights, like this W1 here is shared on multiple locations, how do we deal with that? And to answer this, let's first just look at an unshared weight. So for example, so this is an arbitrary weight in some matrix multiplication in a fully connected layer. So some arbitrary weight in a fully connected layer. And now we first look at how this looks for an unshared weight. And now essentially we can look now at the computational graph. So a neural network is really just a computational graph. And we can now just zoom into this unshared weight. So in the computational graph for an unshared weight will always look like this here on the right. So we are somewhere in our huge neural network and we are now really zooming on this weight W here. So what this weight W does always locally is it gets some output of some hidden unit and it multiplies the output of the hidden unit and it feeds again into the activation of the next unit. So here this is the activation of a next unit, so just accumulate inputs, and in particular the weighted input from this unit here. So if you have an unshared weight, the computational graph always locally looks somehow like this. You have an output of some unit which you weight with W, and this is again input to the next unit. So yeah, the product of H and W, H is the output of the previous unit, W is the weight, gets just summed up in the next unit. And now as we saw actually in the last lecture, so backprop essentially is just a chain rule of calculus. So we saw that we wish to know the derivative of the loss with respect to our weight, and we saw this is just the derivative with respect to the next computational node. So this is this activation, so this sum here, times the local derivative of the sum with respect to W. But now we feed in this product of H times W. So the derivative of the sum after W is just this output of H. So this is what we learned last lecture. The derivative according to backprop of a weight is just the forward message times the backwards message. So in the last lecture we said these weights here sit on this edge, and we just now made this multiplication explicit. And here this shows, again, the principle of backprop. So we have this forward message, backwards message, and the multiplication is the gradient of our W. So yeah, DL after the sum is the backwards message, and the forwards message is this H. So this is actually what we discussed the last time if we have an unshared weight. So just backprop. And now figure that this W is now shared at two different positions in this computational graph. Then this always looks like this. So for a shared weight, which is now shared 2 times, we actually always have the picture on the right. So we have again one unit H, and we have another unit H prime. So this might be somewhere else in the computational graph. And now what happens with a shared weight is just that this weight is used 2 times. So it weights the output of this neuron, but it also outputs the weight. It also weights the output of this neuron. So it just weights, so it's one weight, but it weights the output of 2 different neurons, and this weighted output gets just input to some next neuron. And now we can see what the derivative of the loss after dW is. So again, by chain rule. So this W is now used at 2 locations. And by the chain rule of calculus, we just know that the derivative is just dl after d sum, so after this node, times d sum after dw, so d sum after dw, and plus dl after d sum prime, so after this node, plus d sum prime after dw. So essentially what really happens is that we just compute, so d sum after dw is just h, so the forwards message, and the sum prime after dw is just h prime, so this other forwards message. So all what happens is that we have this forwards message times this backwards message plus this forwards message times this backwards message. So all what happens is just that these two different gradient computations get added up. And for example, the same is also true if we have like a triply shared weight. So it's again just forwards message times backwards message plus forwards message times backwards message plus forwards message times backwards message. So if we have a shared weight, then they just accumulate all these different gradients. So from all the nodes where they are used. So they just accumulate all the different gradients computed at all the nodes where they are used. So this answers the question, how do we learn backprop with shared weights? And in principle, you can therefore apply this also to this tuplets matrix. So the zeros are treated by just not updating them, and the shared weights are essentially just updated by accumulating these different gradients here. And so to summarize this section, so we discussed a few structures and mentioned that this is actually a pretty engineering task and a little bit of a black art. We looked at a few benchmarks, so we looked at MNIST and ImageNet. So on this website, there are a few typical image benchmarks. So MNIST is handwritten digits. Fashion image is same format as MNIST, but showing fashion items instead of digits. Street View house numbers, which are photographs of house numbers. Cipher 10 and Cipher 100, a small scale object recognition task. And ImageNet, one of the most challenging tasks with up to 20,000 classes and millions of examples. And then we discussed backprop. So in principle, you can reduce backprop in ConvNets by, again, to a matrix multiplication like in the multilayer perceptron. However, for ConvNets, the matrix has a special structure, so called tuplet structure. So this typically happens if you look at convolutions. You can always convert convolutions back to a matrix multiplication, and they always have some tuplet structure. And this tuplet structure is sparse, but we can simply respect this in learning, so just don't update the zeros. And the shared weights, we just saw this is simple. It just accumulates all these different backwards messages. And this was just to understanding, so to connect back to these fully connected layers in MLPs. Don't do it this way. This is terribly inefficient. You can just use standard tools which do this for you, like PyTorch and TensorFlow. But linking back to matrix multiplication and multi-layer perceptrons essentially lets us understand how backprop works in ConvNets.